Today I'm bored, so we're going to make an entire machine learning library from scratch in C and train it to recognize handwritten digits with the MNIST dataset, right? But before I get into any of the code, I want to go over just a bit about what it actually entails to create some sort of machine learning framework or library, right? So I would argue that there are three main components of machine learning, or like of a framework in which you need to do machine learning. The first one is some way to do math with tensors, right? And tensors are just like, it's just like an arbitrarily dimensional group of numbers, kind of. It's like you have vectors, matrices, and then those are all examples of tensors. Although today we're just actually going to be working with matrices to make our lives slightly easier in code. And then the second component is that you need some way to find gradients of arbitrary functions, right? You need some way to define arbitrary functions, some way to find their gradients. And then the third component is just some sort of glue layer that ties all the components together, right? Now this might not mean anything right now, but let me just dive a bit deeper into it. So when you have some sort of machine learning model, it's literally just some function, right, that maps inputs to outputs. The inputs could be like the entire history of a chat with like ChatGPT, and the output could be a probability distribution for the next most likely token. It could be a word in one language is the input, and the word in another language is the output. It could be what we're doing today, where you have the input is some sort of handwritten number, and the output is a probability distribution, right? Where the value at that number's index has a higher probability, right? So it's just a function, right? And the key difference between like a function that you might be more familiar with from like a math class and a function that you're dealing with in a machine learning model is that these functions have a bunch of adjustable parameters, right? So you kind of set like some sort of shape of the model, and then you have a bunch of numbers that can be adjusted, right? A bunch of tunable parameters. I think theta is commonly used to denote parameters. If you're familiar with like the classic perceptron with weights, the weights and biases of that are the parameters. So you have this model, and it exists. It performs some mapping from an input to an output, and because of its parameters, there are like a very large number of possibilities for what this mapping can actually look like, right? So that's where the next aspect comes in, which is some sort of cost function, or a loss function, sometimes it's called, which will take in some training sample, right? Some input and some expected output, and the model parameters itself, right? So this is the cost function. And the cost function quantifies how bad the model did, right? So if the model was highly accurate, if the model's output was close to the actual output, then the cost function is going to be low. If the model was very bad, like at the start of training, the cost function is going to be very high. So the entire goal of machine learning is just to minimize the cost function, right? By adjusting the parameters, right? Not good. So the way to do that, because the cost function exists in a very high dimensional space, like even for a simple network like we're going to make today, there are like hundreds if not thousands of parameters, right? So you can't just find the global minimum of the cost function, but what you can do is locally find how to decrease the cost function the quickest. And that's where the gradient comes in, right? Because the gradient of the cost function with respect to all of its parameters tells you in which direction you need to move to change the cost function the greatest, right? Wait, that's actually gradient. It's that way. My bad. But the gradient tells you in which direction you need to move to minimize the cost function the greatest, right? So then that is where the final layer comes in, the glue. So you need some way to define this function with a bunch of parameters. You need some way to automatically, and to find the cost function. You need some way to automatically find these gradients of any arbitrary function. And then you need some sort of glue layer which will go through all your training examples, compute the gradients for that training example, and then automatically adjust parameters based on those gradients, right? So we have a lot of work ahead of us, but let's just start with the basics. We've got our hello world program here. Although today what I'm going to do is actually take the code from my arena video, because we're going to be needing to do some more complicated memory allocation today, and I, to be honest, just do not have the patience to deal with malloc and free right now. So if you're following along in your own language, feel free to use like whatever memory allocation style you're more comfortable with, or you can even watch my video on my 2 videos on arena allocators if you would like, but it's not necessary. It's the arena, and then the other thing I'm going to do is take my random number generation code from one of my previous videos. So this is also something that is not entirely necessary, but here, I want to get slightly higher quality random numbers than you're going to be able to with just the built-in rand function in C. So I'm going to include base. So you see, I made this base file, and then I have an arena header file, and I have a random header file, and then we're also going to get arena.c and g.c, and then I'm going to create our permanent arena here. And because we're going to be loading in large data sets, I'm going to give our arena a significant amount of memory. Alright, and that should be the project setup. I just want to make sure that we are compiling everything alright. Perfect. Okay, so getting back to our outline here, the first thing I'm going to do is just build this math layer for us, right? Like I said before, I'm actually just going to use matrices. If you're dealing with like a production ready machine learning library, like something like PyTorch, TensorFlow, JAX, whatever, it's going to allow you to do arbitrarily dimension tensors, but for our purposes today, the matrices are going to be sufficient. And then I'm going to have a bunch of functions here. So we're first off going to have a function to create it, which will take in an arena, a number of rows, and a number of columns. And then I'm just going to do some helpers here. So I'll have a function to clear a matrix. I'll have a function copy a matrix. We'll have a function to fill a matrix with a certain value. And then getting into the actual arithmetic here, I'm going to have a function to add 2 matrices. And for all these functions, I'm going to have it take the input and take the output as a function or as a parameter to the function, and then return a boolean on whether or not the function was successful. Now, this is not necessary. You could have it return a matrix, but in my case, I think I prefer the ability to control when the matrices are allocated and on which lifetime they're allocated. But again, feel free to do whatever you want. Oh, another function I'm going to do here is have a function that scales a matrix in place. Here, we'll just put these all on the same line. We're going to have a matrix multiply function. And then I'm going to have a few more arguments here. The first one is whether or not to zero the output. So if that argument is false and you don't zero the output, then it's going to add the matrix multiplication of A and B to out. If you do zero the output, then out will just get set to the matrix multiplication. And then we're also going to have 2 functions here on whether or not to transpose A and B. And I've gotten some questions in previous videos about like 8-bit booleans versus 32-bit booleans, and honestly, the fact of the matter is that it doesn't actually matter in most situations. Here we might be saving some memory in terms of argument costs, but it might even be more assembly instructions to use 8-bits versus 32 bits here. Honestly, I would just go on Compiler Explorer and look if you really care, but it's not going to make a huge difference either way. And then another thing we're going to do here, because we're doing some machine learning stuff, I'm going to add a ReLU function. If you're not familiar, it stands for rectified linear unit, and it's just 0 if your input is less than, if your input is negative, and equal to your input if your input is positive. So it's also just equal to the max of 0 in the input. And that's going to be one of our activation functions here. And then I'm also going to add in the softmax function, and that converts your input vector into a probability distribution, although we'll get more into the implementation of that in a second here. And then we're also going to do, I'm going to add a cross entropy function here. Now this is going to be our cost function. And this is the cross entropy loss is specifically good for dealing with probability distributions generated by softmax. So this function, it'll take in some expected probability distribution P, and some actual probability distribution Q, like so. And then one more, the next thing, final thing, is I'm going to add functions to get the gradient of each of these, of the activation functions and the cost functions. So the gradient of the ReLU will be, just take that, and we're actually going to call this function, it'll add the gradient of the ReLU. And this would go for, this one will take in the output of the softmax. And then finally, we're going to do cross entropy add gradient. And then this will take in the same arguments. So, all right, so this is our interface here. And we're just going to write in all of these functions in plain C. I'm going to write them in. But if you're dealing with an actual machine learning library, these are going to be the functions that are going to be run on the GPU, right? These are going to be the things that you want to hyper optimize, especially that matrix multiplication. But I mean, computers are still fast, and we still will be able to do relatively complicated networks just on the CPU. But just so you know, like in the real deal, something like Jack, something like PyTorch, these are going to be the functions that are actually run on your GPU. All right, so now to implement them, I'm going to get started on map create here, and on the right here, I'll pull up just our definition there. So because we're dealing with arenas, it's pretty trivial for me to actually allocate the arena structure onto the heap as well. Now, you might not want to do this if you were dealing with malloc or a different allocator, where it's worse to make many small allocations. But in this case, just the ease of dealing with pointers for me outweighs the slight memory cost. But you know, you do. So let me set the rows and columns, and then map data is going to be push array onto the arena of size rows times columns. So here, let me move my mouse. Okay, and for the map copy here, we're gonna do. This is just, well, first off, we need to check. Yeah, this should actually return a boolean. And this is going to, first off, I'm going to check if the shape of these is the same for destination columns. And then we're just simply going to do a mem copy here onto destination data from source data. And then it's just going to be size of F32 times destination rows times destination columns, like so. Mat clear, this one is just going to be a mem set 0. Same thing with size of F32. Okay. And then this one, I'm going to grab the size from the matrix, and we're just going to do this in a for loop. So I'll take the rows times the columns, and then we'll say for I is less than size, mat data I equals x, like so. Oh, actually, one function I did forget to add earlier that I'm going to put right here is going to be mat sum, which will just calculate the sum of the matrix, but let's start off with scale here first. So I'm actually just gonna copy all of this function, and then instead of doing that, we're gonna say times equals scale, like so. And then same thing, there. And then this one, the sum, we're gonna have, I'll take this out here. And then sum plus equals, return sum, like so. Get rid of that. Okay. Now we're dealing with the actual matrix arithmetic functions here. So for add, first off, I'm going to check that A and B have the same size. And then I'm going to check if out and A have the same size, right? And by transitivity, it should all work out. Now, what you could do if you wanted to, and I don't know, I might do this if I was trying to build a more robust application, is you could have it so that matrices also have another parameter here called like alloc or something, where it's the amount of data that they have allocated, and you could dynamically adjust in these arithmetic functions the size of output given that it has enough, like if it has enough of an allocation to hold the output. Again, this is kind of you to you. I'm just going for what is simplest right now, and because we're going to be hard coding everything and each variable will have its own thing, this is the simplest right now. So I'm also gonna take a size here, which would be out rows times out columns, and then we're gonna go for I equals 0, I is less than size, out data I equals A data I plus B data. And then for sub, it's going to be basically the same thing, except for obviously this addition here, it's going to be a subtraction. And then, so matrix multiplication, this one is going to be a bit more involved here because we have those transpose values. So the first thing I'm going to do for our size checks is to get the transposed, post-transpose the number of rows and columns in A. So if we are transposing A, then A rows is input A is columns, else it's A is rows. Did I misspell something? Oh, I did misspell that. Transpose. And then A columns, that's going to be columns, that's going to be rows. And then this is going to be same thing but for B, like so. And then, so if the number of columns in A is not equal to the number of rows in B, then we cannot multiply the matrices. And then if the output does not have the same number of rows as A, or the output does not have the same number of columns as B, then we cannot multiply the matrices. Alright, so now we're going to do, then we'll check if 0 out, then we'll call mat clear on out. Now, what I'm actually going to do is I'll create 4 functions here that are for the 4 variations we could get of transposing. And this is so that each function can be as performant as possible, right? So we'll say matmul impl, or I'll just call it matmul, and then I'll do n to denote that it is not transposed, and then t to denote if it is transposed. So there's this function, and then we're going to have 4 of these, so t, like so. And then what I'm going to do is I'm actually just going to create an integer here that stores, I'll take transpose A, bit shift it once, and then OR it with transpose B. And this is so that I can do each of those 4 cases just in one large switch statement. And this is kind of a trick that I like to do in any situation where you have like two booleans and you're doing something different for each of the four cases. So for this one, we'll call matmul so. And obviously, you don't need the squiggly braces here. Obviously, I prefer whenever I'm using switch statements to have a new scope for each case, but it literally does not matter right now. Okay. So for output, what I'm going to do for this one, we'll just start with our basic for loop, and I am going to use 64-bit integers here for each of our counter variables to make sure that we never overflow when doing the math to determine the one-dimensional index from our two-dimensional index. Also, I should point out, I am going to be doing everything row major here. And then, okay, so for our inner loop, A is less than A columns. So now we're going to do out.data at, so it is going to be at the jth column, or the ith column in the jth row. And that's going to be plus equals A data, which is at the same row, and then the kth column. Am I doing this right? B, which is at the same column, but the kth row. So, I think normally I'll have I going for rows. So, let me just switch that real quick. So, B is going to be at the same column, so the jth column and then the kth row, like so. And then if you've seen my first video, you'll know that we should actually swap these two for loops to have the best cache locality for our function here. Okay, so now I'm going to copy this and I'm going to modify it. So here, I'm actually just going to copy this all 3 times here. Like so, okay. So for this function here, this kernel, we have B is transposed. So literally that just entails swapping those two variables, right? So it's transposed. And then what we're going to want to do is correct the order of the for loops to get the best cache locality. Now that we're iterating J here, we're going to want to move the J for loop up. Okay. Now for A, again, we're going to swap these two. And then we're also going to have to swap this loop variable because this was based on this needs to be based on the transposed A. And then now taking a look at this, it seems that 2 of these variables are using K. Going to move K up and I down so that we have the best looping. And then here, so we're going to have to swap both of these actually. Like so. And now there isn't actually like a best loop order here. So we'll just go IJK. And that should do it. That is how you do the simplest, although still modestly performant, matrix multiplication. And honestly, if I'm not mistaken, a lot of the issues that you run into that the more advanced matrix multiplications solve, like cache thrashing and stuff, we're not going to run into because our matrix multipliers are going to be really small in this example. But I could be wrong about that. Okay, so now to do the activation functions here. Although these ones that calculate the gradient and stuff, I'm going to leave that till a little bit later in the video so that it makes a bit more sense when we cover the math behind all that. And let me just start off with the size checks here. But like I said before, ReLU stands for Rectified Linear Unit. And it is literally just the max of 0 and x. So in other words, when x is less than 0, it's just y equals 0. When x is greater than 0, it's y equals x. It's just a straight line negative and then linear when it's positive. And I believe the ReLU activation function became popular like a while ago, but it wasn't the de facto activation function for a while. And I think actually now you even have slightly more modern activation functions like JLU or You can even do like leaky ReLU or some sort of exponential ReLU. But the original one is still great. I believe it fixed the vanishing gradient problem, or at least helped the vanishing gradient problem from the previous de facto of the sigmoid function, but that doesn't even matter because it still works for our purposes. And then the softmax function, what that is, each term, so the output at some index I is equal to e to the input, we'll call it a, over the sum over all e's to the input, right? And you'll see what this does is actually twofold. The first thing is that because we're exponentiating each term, it makes sure that everything is positive. And then because we're dividing by that sum there, it also ensures that the sum of the output will equal 1, right? So those two factors, each term being positive and the sum being 1, means that in the end we have a valid probability distribution, which is the goal, right? So I'm just going to loop through, and then starting off, exponentiate each term, and then also add that to our sum, and then we're going to get our scale, or actually I'm just going to call mat scale on the output, and that's going to take 1 over the sum, like so. And then, so cross entropy, this one works on a probability distribution where P is the expected, this is our loss function by the way, P is our expected probability distribution, and then Q is our actual output, or actual probability distribution. And for this one, first off, I will do some size checks. So all of these should be the same size. Then same thing for out. So if out rows doesn't equal P rows, or out calls doesn't equal P calls, return false. And then what this is, it is the sum, the formula is just P times the negative log of Q. Although I believe what you would actually want is the sum over this, but I'm just going to put each term into the output vector. I don't know if that's technically correct, but it's going to give us the correct gradients for our purposes right now. So loop through I less than size. And then I'm actually going to do a check. Well, here, I'll say out.data I equals, and then I'm going to check if P is equal to 0. If so, just set it to 0, and if not, we'll do P times negative log of Q. And that should do it. Okay. So for now, that's it. Okay, we got through it. So this is just our basic, our backbone, the math library, right? Although one thing, I'm going to take a quick detour here and actually open up a Python file so that we can have some way to get our MNIST dataset. So for this purpose, I'm going to use the module called TensorFlow Datasets. I'll import that as TFDS and then also import NumPy. And it's a pretty simple interface. All we're going to do here is we'll have a training and a testing dataset, and that's just tfds.load MNIST, and we'll say our split is equal to train and test, right? Like we have over there. And then I'll say as supervise equal to true. So that would load in the data set, but it doesn't actually give us the format that we want. Right? The goal here, I'm actually just going to output 4 files here. One for the training images, training labels, testing images, and testing labels. So I want to be able to convert from a data set to just a standard NumPy array. And then I'll take in a data set. And honestly, I'm sure there is some Python magical way to do this quickly. Or okay, I think we're back. Sorry, I had some recording issues. Anyway, so like I was saying, I'm just going to iterate through the data set here and add each label and image, and then return np.array of the images and the labels, like so. And then, so we're going to have train images, train labels equal to ds2 numpy of the train data set, and then same thing for the test. And then the next thing we need to do is ensure that these are in the correct data format. So I'm just going to call as type and then np.float32 because I'm just going to be outputting these to a file. And then the other thing is that the images are from 0 to 255. So I'm going to convert it from 0 to 1 just because the normalized, I believe, works better for machine learning stuff. And so the other thing here is that the labels right now are not using what we call one-hot encoding. They're just like if the number is 4, that the training label is literally 4. But I'm going to do the conversion to one-hot encoding in C. So now what we need to do, I'll say train images.to file, and we'll call this one train images.mat. And then same thing for all of these. So we'll say labels. And then the last thing I'm going to do for each of these is print their shape so that we know we know what shape to load them in with in C. So again, this is hard coded. If I was doing this in an actual project, I would probably want to make my own file format or use some existing file format that includes size information, and also one that might even include compression, right? But we should now see that we have these 4 files here that include our data, and then you can see these are the shape of our array or our matrices. So now coming back in a main here, what I'm actually going to do is have a function called matload that'll take in a size and then a file name to load the file from. So with this one, what we're going to do, first off, we're going to say that our mat is just the create function to create that. And I misspelled arena. That's a new one. Okay, so then what we're going to do is I'm actually just going to open the file using fopen. And I got some, in a previous video I mentioned that I don't love using fopen. And honestly that's just because it gives me less control over how I'm loading files. That API is just another additional layer over the actual over the actual operating system's doings. So I usually roll my own, but in this case we literally just need to read the entire file, and this is going to work perfectly fine. If you're not familiar with the API, this is just a quick trick to get you the size of the file, just because I want to ensure that we're not reading too much. So I'm going to say we're going to read basically as much as we can if our file's sizes were mismatched, right? And then we're just going to call fread, and we're going to read into mat data size from mat, and that should do it. So now here in main, I'm finally going to load in, I'll say, our matrix for our training images. That's going to be on the permanent arena, and then we're going to have 60,000 rows and 784 columns. So this is going to be a bit clunky, but basically each row of it is going to be one training example. This is just easiest because of how the data is laid out in the file, but you know, feel free to do it however you want. Okay, and then alright, so that's that. I'll deal with the training labels in a second, but what I'm actually going to do here is I'm going to have a helper function, I'll put it down here, that will draw an MNIST digit into the console. So we're going to take just the data there. And what I'm actually going to use here is what's called ANSI escape codes, which I believe is a bit of an older terminal thing, but it's basically just special characters you can output to the terminal that control certain aspects of it, like the color or the positioning and stuff. So in this case, also, if I forgot to mention, the MNIST digits are 28 by 28 pixels. So I believe we're going to do 48.5 and then color. This should set, so there, I'm kind of just doing this off the top of my head, although I've written this code before, obviously, where there are 255 like built-in colors to the console, and this allows you to set the background color for one of those. And in those, the 232 to 255 are grayscale. So if you go 232 plus the number which is between 0 and 1 times 24, then we should get a nice grayscale image. And then one final thing I'm going to do here is reset all the color information at the end there. So now if we call draw MNIST digit on train images data, and this will just draw the first one in the training set. And if I remember correctly, first off, that's going to annoy me. So I'm going to define CRT secure no warnings. Yeah, and if you're wondering, fopen is crossed out because it's technically not secured. And there's like in theory, better version. But again, does not matter for our purposes. And would you look at that? That is a number. We can even do, if you do like plus 1 times 748. 748 is just 28 squared. If you worked with MNIST long enough, you'll know that one by heart. So you can see we got these images loaded. Pretty cool. Okay, so we got that working. Oh, and then the one more thing I'm going to do here, and I'm actually going to give us another scope. Although I'll first say that our train labels is just mat create. And in the training set, there's 60,000 examples, and then each has 10 tests. And like I said, so the numbers that we would actually load from the file, which I will do now, are literally just the actual number. So it's a 60,000 by 1. But what we want is to have a probability distribution of the output, and that is called one-hot encoding when you have it like this, when there's only one correct answer. So literally what I'm going to do is just loop through first off the training set, so 60,000, and then we'll say that our train labels data at I times 10 plus we'll say the num is equal to train labels file.data at I. So I plus num equals 1. That'll do the one-hot encoding for us. And then do the same thing for the test labels. And grab another thing there. And that should do it. So now we can go, if we draw the MNIST digit of our train images, I believe that was a 4. And the other thing I'll do here is print the first 10 numbers from our train labels set. And we should see that there are 0 everywhere except for of the 4th index. Alright, and would you look at that? So 0, 1, 2, 3, 4. 4th is 1. That is one-hot encoding complete. Okay, so we have now successfully crossed number 1 off the list. We've completed the math section that makes this work. Now what we need to focus on is how we can find these gradients, right? Remember from a long time ago, I said we need some way to programmatically define our function and our cost function, and then some way to automatically find the gradients of those functions with respect to our parameters, right? So let's talk a bit about how to differentiate, right? So again, there's 3 methods that I believe I'm aware of right now. So the first one is numerical, right? This is just your classic finite difference, right? F of x plus h minus f of x over h, right? Like, just literally doing it. But this is bad, right? In this case, it might not be that bad. But when we're dealing with our parameters that might have like thousands of numbers in them, right? These exist in many dimensional space. To find the gradient, we would need to take a little step in each of those dimensions and compute the entire output, right? So numerical is out, right? The second way we can do is called symbolic, right? And if you're familiar with something like Wolfram Alpha or like Mathematica, something like that. Like if you're doing your Calc 1 homework and you look up how to derivative, like this is what I'm talking about when I mean symbolic, right? Like you give it some sort of like input string, right? F of x equals x squared, and then it literally produces the symbols that give you f prime, right? And this one does work, but it has a few disadvantages. One, it's really complicated to program, at least I would assume, because you have to like have all these rules. Like you're literally just implementing every derivative rule and then simplifying it. And two, you can come in, I forget what the exact problem is, but essentially you just have a large number of symbols, especially when you're deriving multiple times. So kind of complicated, kind of cumbersome, not going to do that. The third method, this is specific to computation. I don't know what the specific name for it, but I mean PyTorch calls it AutoGrad. I'm just going to call it AutoGrad basically. And this method is actually pretty cool. What you do is, given some function, let's say we just have like a classic like mx plus b, right? What you do is you define a computational graph for that function. So we have some m, we have some x, right? And we'll say we have some like intermediate variable z here, and then we also have b, and this finally gives us our output, right? So we take this computational graph here, and then from this, we're able to compute the gradients of our inputs, or even like our parameters m and b, with respect to f by traversing this graph in different ways. Now there's 2 ways to do it generally. There's forward mode and reverse mode. Today we're going to be doing reverse mode, but it doesn't really matter. So this is what we're going to get started with today. Is figuring out computationally how we can create this sort of computational graph that we can then traverse in both directions. Well, like obviously if you traverse it this way, you're going to be able to literally compute the product, like what f is, given your parameters, right? And then when you traverse it the other way, we're going to be able to compute our gradients automatically. So, actually, one more thing I want to mention. If you have some background in like basics of how perceptrons work, then you would be familiar with the backpropagation algorithm, right? And the backpropagation that you do for that is I believe just a strict subset of automatic differentiation, right? Because the way we're doing it this way, where we have the full computational graph, we'll be allowed to have like arbitrarily complex relationships between each of the variables, right? Whereas in when you're dealing with just a basic perceptron here, right? Like here, if you have just a basic linear perceptron like this, right? It doesn't allow for something, for example, like a residual connection. Like, I believe that's very common in transformer architectures nowadays, is to have the output of one layer just be added directly to the input of itself, right? And that's the kind of thing where if you have the computational graph of that, it's easy to automatically derive it, but it's not like the researchers who made ChatGPT are literally finding gradients by hand, right? just because that part confused me for a bit. And actually, I know I mentioned in a previous video that I made a machine learning library with a pretty fatal flaw, and that was the reason. It was because it didn't work with computational graphs. It just worked linearly, so you couldn't have residual connections. So the first structure I'm going to make here is, I'll just call this one, I'll call it model var, for like model variable, and it will have an index, and then it will have a matrix for its value, and a matrix for its gradient, and then also, I should probably put this up here, flags. I mean, yeah, like if I put the U32 down here, that technically means the structure is bigger, but you don't have to worry about that right now. And then I'm gonna define the flags here. So the first one here, I'll say me flag none. So the first flag I'm gonna have is requires grad for requires gradient. And I'm gonna make the flags are gonna be a bit field, and then the next flag is whether or not it's a parameter, right? A parameter of the model. And then we're also going to have input. And these are just to denote like specific variables that we might care about for a model. So we have input, output, and then I'll call this one desired output. So that's used obviously when computing the cost. So desired output, and then finally, and honestly probably most importantly, is the cost, right? And then here I might just align up all these so it looks nice. Perfect. All right, so those are our flags. The next thing we're going to define is another enum here for the type of operations that it could have, right? So this is like how the variable was created, right? So obviously it can just be created, like you could just instantiate it, but you can also have like unary and binary ops. So I'm actually going to create these, I mean, they're not really private, but like internal enums that denote when the start of like each operation type is, so that we can, from just the operation, know how many inputs the variable had. So the only unary ops that we actually have are just our activation functions. And honestly, I don't know. Like, I don't know if it's the best thing to have activation functions be operations themselves. Like, you might want to go slightly more granular than that. But for today's use cases, this is going to be just fine. And it's going to make our lives slightly easier. And then I'm literally just going to take a look at each of the ones that we have here. So we have mvop add, mvop subtract, and then we're going to go mvop matmul. And then I'm also going to add cross entropy loss there. And that should do it, okay? Oh my god, I cannot vim right now. And then I'm also going to define a macro here that, given an operation, will return the number of inputs. So basically, so if the op is less than mv unary start, then it has 0 inputs. Otherwise, if the op is less than mv binary start, like so. Here, let me wrap this in parentheses to make it slightly more clear. If it's less than binary start, then it's going to have 1 input, else it's going to have 2 inputs. Okay, so now we have a model where ops, we have an op, and then we have a, let me add a name here. A inputs. I'll define mv model var max inputs. And okay, so that is our model variable. And then also the index, I don't know if I mentioned earlier, that's going to be useful later in some operations. So the next thing I'm going to make here is a model context, which this is like going to be the structure that you, I mean, as much as you could consider it the model, it is the model. So first off, it's going to have a number of variables, like the current number of variables instantiated on it. And then it's going to have a matrix for the input. It's going to have a reference to the input, output, desired output, and cost. Yeah. And then the next thing I'm going to define, if you remember, I believe I said that machine learning is metaprogramming, right? So literally I'm going to have a structure called a program that is going to be a like quote unquote compiled version of some computational graph here, right? So instead of traversing the graph structure while doing the computations, I'm going to traverse the graph structure and then produce a list. So like for this case, it would be like we would evaluate M, then evaluate X, then evaluate Z, then evaluate B, then evaluate F, right? So like if we do the evaluations in this order, we will compute the output, right? You can, I mean, I don't know if something like PyTorch or whatever actually uses like some kind of like intermediate representation or literal bytecode, but you can think of this kind of as like our bytecode because the ops are encoded into the variables themselves. It doesn't even matter, or it does not matter that much. And then we're gonna have two programs here. We're gonna have one for the just the actual normal output. I'll call it the forward program, and then one that produces the cost, right? So remember, we have some actual function here that we're trying to make good, and then we also have some cost function, which is the thing that we're optimizing on. So that means that we need our two separate programs here, okay? So that's that, and then so now we need to actually define our interface for using this. So what I'm going to do, I'm going to have basically for each operation that we can do, I'm going to have a function that creates a model variable, right? So we'll just start with our basic create function, and this will take in an arena, a model context, a size, and also a flags variable. Function. Okay, like so. And then we're going to basically, for each operation that we can have, I'm going to have a corresponding function here. So model var will have MV ReLU, and this will take in an arena, a model context, and then an input, and then also some flags, right? And also, well, it reminds me of it's very wide code. I forget, what's the guy's name? Estiel something. He had a video where he talked about loving wide code. We're gonna end up with some wide code today. All right, so that's for ReLU and softmax, and then we're gonna have here. Actually, I'll just take 4 of these lines here. For our add function, this is going to take a and a b, and then actually we only need 3 of those, so we're going to have sub matmul, and then cross entropy, and this one I'll call these ones P and Q, like so. So that's that. Okay. So now we need to go here, take these functions, and I'll implement all of this below our previous thing. Okay, so now for create, what we're gonna do is just first off, I'm just gonna push the var onto our arena, and then going to get the index given the model's current the model context num vars, and then I'll also increment that. And then we got to fill in out.flags equals flags. And then we're going to say out.value equals map create. Now, like I said before, this is just a computational graph that we're building here. We're not actually doing the computation right now. So if you wanted to delay making this arena until you're actually compiling it, your computational graph, into the program itself, you could do that. Our solution today is not going to be terribly memory efficient, right? Because we're going to have all these intermediate variables here that could in theory be used in the same memory. Like you could, this Z variable here, the memory for Z and the memory for F do not, could be the same, right? But just to make our lives easier today, I'm going to make it all separate. I'm just trying to point out a potential optimization you can make. But on our scale, that does not matter. And then I'm going to check here if we have a requires grad. And then in that case, I'm also going to create our gradient vector, like so. So that's done the op and the, okay, and then here, let me say out op equals op. And I forgot to include that as one of the arguments. We're going to have a model ops, or I'll just call that op. Yeah, I guess ops doesn't really make sense for the enum name. Okay, so fix these parameters and then we should be good. So think of us the ops inputs. Okay, perfect. Now what I'm going to actually do is I'll create a helper function here that does a simple unary operation. So this will take in that input, and then it'll also do a operation. So model op. And in this case, all of these are going to be the same size, but what I am actually going to do is include a rows and a columns in with this, because you might have a unary operation that changes the size of the output. So in that case, you might want to do that. So when we create, this is going to take the arena, the model, the rows, the columns, flags, the op. Although the one thing I am going to check, if we have our input, if our input flag requires gradient, then I'm going to override the requires gradient in the current flags, right? Because basically anywhere downstream of a variable that requires gradient, you also need to have the gradient, because the gradient is with respect to the output. And then we're going to say our inputs is equal to input, right? And then now all we have to do here is we'll call mv unary impl, and then we'll go model arena input val rows input val columns, and then flags, and then our op is mv op relu. So we're going to return that, and then let me just clean this up a bit. Okay, so that is for our relu function. Now obviously a lot of this code is kind of tedious, so just bear with me here. So this same thing here, but instead of relu we have the softmax operation. And then similar to the unary impl, I'm going to make a binary one. And I suppose you could also make these macros if you wanted to. It wouldn't have a huge difference. I just think functions are slightly easier here. So I'm going to do or b flags, and so if either of the inputs requires gradient, then the output should require gradient. And if you want to be a bit more thorough, you could check if, like, technically this is going to return a value greater than 1. You could, I think the more accurate version would be like equals MV flag requires grad, but I think this should work here either way. A inputs 1 is B, and that should be good for that. Oh, actually, you know what I did? I forgot to do, in our MV create function, I want to check the flags and then fill in these 4 variables if we have hit any of those flags. So if flags and MV flag input model input equals out. This is nice. Oh wait, these should be model variables. So if we're going for output, our model's output is such, desired output, like so, cost. I spelled it wrong, desired output. Oh, I spelled it wrong here. Alright. And then this is going to be the cost. Alright. There we go. Sorry, my apologies. If you can't tell, I've been coding for a long time. Okay, so now our add here is this is going to return MV binary info with our arena model AB. And then for add, it's just the same thing. Although, actually, we should probably check. And we don't have a robust error handling system here. Again, real library, you would probably want to make sure that you can deal with errors in a more graceful fashion than just returning null. But right now, I'm just going to return null. Okay, AB, and then we got a model, and then we're going to go for eval rows, eval columns, and then our flags, and then MV op add, like so. And then for our sub here, we're going to do the same, but just replace this with sub. And then, funnily enough, our cross entropy is actually more similar to add and subtract. We're just going to have to replace A with P and B with Q. P, Q. And then this is cross entropy, like so. And then, so, right now, for our mat mul, we're going to do if A's columns doesn't equal B's rows, and that's the only check. And then it's going to be A's rows and B's columns, and then mat mul. Alright, so this is the backbone of our thing. That is the interface for dealing with the model variables themselves. And I'm going to go eat dinner and then come back and finish this. Oh wait, actually, so coming back here, one quick change I'm going to make. I'm just going to remove this op argument from the MV create. It does not make sense because this op is just going to be the creation, and then in the info functions themselves all set the operation like so. Alright, so now we're actually done with the model variables, and then what I'm going to do next here is work on the functions for the program and the context itself. Okay, so let me switch screen. So we're going to do, I'll have a function, okay, model program. This one will be called, this will use to create a program. So to do that, we're going to need some sort of arena. We're going to need the model context itself. And then also I'm going to have an output variable. So this will be like what variable specifies the output of that program. So for our forward program, that's going to be whatever is literally the output. And then for our cost program, that's going to be whatever variable is the cost, right? And then I'm going to do model program execute. So this will be context. Actually, no, it doesn't even need to allocate memory. This one, because the program itself has references to the variables, all this needs is the actual program. Or I could call this one, I'll call it compute. And then this one can be compute grads. So you'll obviously have to call compute. Well, this isn't obvious, but you will have to call compute before calling compute grads because of how reverse mode works. So you might want to add a check for that, or like some way to verify that that's happening properly. But I'm not going to do that right now. Right, so now we're going to do arena. This will be a function to create the model, and then we're going to have additionally a function called model compile. And this is the function that will actually create our two programs that we need here. And then we're going to do is have a model feed forward function, and this we'll just feed the input for. So feed forward, another word, is just like run the function. So it'll just directly reference the input and put it directly into output. And actually, one more thing I'm going to do here is I'll call this one model training programs. For let's say training description. Hopefully my header was not covering that. Okay, but so this is going to be a structure I'll pass into the train function. So that needs a matrix to be train images, train labels, test images, test labels, like so. And then also some hyperparameters. So we'll specify a number of epochs. We'll do a batch size. If you're not familiar with this language, we'll go over it in a bit. And then also have a learning rate. And that is not how you spell rate. Okay. So now we're going to have a model train function. This will take in a model that has to be, well, actually for each of these, feed forward and train, the model has to be compiled. So again, probably worth it in a real context to add a some way to ensure that the model has actually been compiled. Yeah, okay, so that's the train function. That should be good. All right, so I'm gonna get started here on our program functions. So for that, yeah, let's just start off with the create function. What the goal of the create function is here. Let me pull up our little thing here. So we're gonna have some computational graph. Let's say, let me do a real example. So let's say in a basic feed forward network, your output for some layer n is equal to ReLU of the weight in that layer times the output of the previous layer plus the bias in that layer, right? And then I'll call this multiplication term, I'll call this Z0, or actually I'll call this Z sub A, and then this whole term here I'll call Z sub B, okay? So if we take a look at our computational graph, what we're going to have is Wn an minus 1, these combine to get Za, and then Bn, these combine to get Z sub B, and then Z, and just the ReLU, right, to get A sub n, okay? So the way that we're going to do this, as we've set it up now, each of these variables has a reference to their inputs, right? So A has or Z would have a pointer there and there, ZB would have a pointer here and here, and A would have a pointer there. So what we need to do is what's called topologically sorting. So this, in computer science terms, is a directed acyclic graph, right? So it's a directed graph, meaning that the nodes have some order to them. it's acyclic, so there's no loops. It's not like we can have A pointing to B and stuff or whatever. Which actually should probably, the code we're going to check does not check. The code we're going to write does not check if there are cycles. Again, real library, make it better than what we're doing right now. But for this purposes, it's fine. Yeah, so it's a graph. And a topological sorting of a directed acyclic graph basically means that you have resolved any dependencies before you, before you get to a node, you have resolved all of its dependencies. So these arrows are actually a bit deceiving, right? That's how we were representing it computationally. And the reason for that is because you can only have like one or two inputs to a thing, to a variable, but a variable can be used arbitrarily and many of times, right? So what we really want to think about in terms of forward in terms of computing the output is the arrows going this way, right? So in that context, one topological sorting could be Wn, then A of n minus 1, then Z of A, then B of n, then Z of B, then A of n, right? So if we look at this order here, we know that Z depends on these two, and then ZA depends on those two, ZB depends on these two, right? And then A depends on ZB. Yeah. So anytime that one of these nodes has a dependency, whatever it's dependent on gets resolved first, right? Okay, so the goal of our program create function is, given our computational graph, and remember, we're getting it in kind of the opposite direction of how we would imagine it. We need to produce that topological sorting, right? We need to produce this array of variables, right? So how are we going to do it? There's like two primary ways to do topological sorting, and one of them is called Kahn's algorithm, and then the other one is with a depth first search. We're going to use the second one, and the reason is because it allows you to more easily deal with a subset of the graph, and that's what we want to deal with right now, because we're only like our costs and our output graphs are going to, our cost graph is basically a strict superset of our output graph. So we want to be able to also topologically sort the subset of the graph. Don't worry about that if that didn't make much sense. But the first thing I'm going to do here is actually grab a scratch arena. And if you want to learn about what these are or whatever, I recently made a video about that if you want to check it out. And then we're going to keep track of whether or not we have visited each node in the graph, and then we're also going to keep track of a stack for like our searching, and then a final output, right? So I'm going to start off with our visited array. Now, obviously, I'm going to use 8-bit things here, although you could get the actual memory usage down a lot if you wanted to do a bitmap instead of a list of booleans. It doesn't. I don't think it actually matters that much. Like, you're not using that much memory for this. And then we're going to have a stack size. We're going to have an out size. And then we're going to have a model variable array for the stack, which is, we're going to put that on the scratch arena. And then this size is going to be num bars. And then we're going to have a out, which is push array. All right, so let me return to this graph here, and I'm actually going to go back to when I had the arrows pointing the other way. All right, so because this is what we're actually dealing with right now. We're starting at A of n, and the output we want to produce goes Wn, A, n minus 1 in any order, then these two in any order, and then so on, right? So, and I want to do this non-recursively, so it's a bit more straightforward. So the way we're going to do this, we're going to have our search stack, and then our visited list. And basically any time that we get to a node. We're going to pop it from the stack, and then, so yeah, this is going to be our search stack. Actually, here, let me say, let's say that we're at ZB. Let's say we're starting at ZB, and our search stack has ZB. Okay, so we pop that from the stack, and then we mark ZB as visited. We've said that we've visited it, and then we push it back onto the stack. Okay, and then we push both of its children onto the stack. Okay, so we'll push BN and we'll push CA, and we'll deal with all of those and so on, right? And then by the time we get back to ZB, let's say we've done all that searching, we're back at ZB. Now we're popping it off the stack again, but we know that we visited it, right? And because we visited it, we can move it from the stack to the output and add it to the output. Hopefully that makes sense. It's a bit weird to wrap your head around, but the code is pretty straightforward. So first thing I'm going to do is just add our root to the output, right? And then I'm going to say, while our stack size is greater than 0, in other words, while we still have a variable to pop from the stack, our current variable is stack size. If you're not familiar, when you do minus minus or plus plus before, that returns the variable after it's been incremented or decremented. And then when you do plus plus or minus minus after, it returns the variable before it's been incremented. So this is just some time saving measure, or like character saving measures, I guess. Alright, so then we're going to do, well, first I'm going to check, this is where we're using those indices that we created. So if our index is greater than or equal to our numVars, like if somehow we have an invalid index, I'm just going to continue because we'd end up hitting an array out of bounds. And then what we're going to do is say if we have visited the current one, right? We're going to add it to the output and continue, right? That's all we're going to do if we visit it. If we have not visited it, first is that we're going to set the current one to visited, and then we're going to add the current to the stack. But now we have to deal with its children. So, or its inputs, really. So I'm going to get num inputs, and that is equal to the macro we made earlier, given that operation. So for each input, so for each input, and we're going to all have model bar input equals cur inputs I. If the input index is invalid, or we have already visited the current index, continue, don't discard that. Else, we're going to push it onto the stack size. Push it onto the stack. Although, there's a slight issue with this implementation, and that is because I've limited our stack size to the number of variables, and there are situations you can run into where you're going to be pushing the same variable onto the stack multiple times. So this is not the most efficient solution, but what I'm going to do is actually check to see if this variable is already in the stack, and if it is, remove it from the stack. So if stack j equals input, then I'm going to loop through and remove it from the stack. So actually we can say, yeah, so stack at k is stack. Again, this is not efficient, but it does fix that issue. And this is just because I have to make the stack have a fixed amount of memory. And that should do it. So now, oh, and one more thing. The reason that I put the output onto the Scratch arena instead of the actual arena is because we might be using a subset of the graph, whereas that's enough memory for the entire graph to be included. So the actual output, we'll call this size is out size, and then the bars is push array. This can be non-zero onto the actual arena of out size, and then mem copy to program vars out. and just return that program. All right, so that's the program. All right. Okay, so just one small thing I'm actually gonna do here is make sure that our out size is less than our number of variables. Again, probably won't happen, but here I'll add that for the stack size as well. So if you were actually doing proper error handling, this would be where you would put an error. Okay, so that's that. And then let's move on to the compute function. So what compute is going to do is basically loop through your, or like execute your program in the forward direction, right? So we're going to go for each variable in the program. Our current variable is, all right, and then I'm going to just grab the inputs here as well. So we're going to have model bar A equals, actually wait, no, we just grab these, because if the inputs, like if the number of inputs is not correct, then we're just not going to access those anyway, so it doesn't even matter. Okay, so now we're going to do the switch on the operator, and then let me just do the base. Let me pull up all the operators. So if we have op null, or we have mv op create, we just safely break out of those, and then I'm also going to include the unary start. And the only reason I'm going to be explicitly breaking out of like the nulls and the unary starts is just to make sure that we're properly handling each case and getting warnings on everything. And the op relu. So relu is just going to call mat relu on the input value. Like so. Same thing for softmax. So softmax is going to be mat softmax, like so. And then we're going to have the mv op binary start. Okay. And then we'll go for mv op add. And that's just going to call mat add. And mat add will take current value, a val, b val, like so, and then sub, and then this is going to be matmul. And the only reason, this has a few more arguments. So we're going to 0 the output and then not transpose either of these. And feel free to use true and false. I'm just slightly more, that will be slightly more compact code-wise across entropy. The only reason I'm specifying that it's matrix multiplication is that you might have, down the line, you might add like component-wise multiplication. And then we'll go for mat cross entropy, and that will be cur val, a val, b val. Should be good. Alright, so thus far we haven't done much too exciting, but now it's time for the real, the heart of why this actually works. This compute grads function, right? So let me go back to our thing here, back to our graph. Now, what we want to do, the goal of, if we go all the way back up to the beginning here, remember, we have this cost function and these parameters, and the goal is to find the gradient of the cost function with respect to each of these parameters, right? So, given some here, I'll even add a y here, and then our cost is based on a and y, right? So, like, in this simple network here, our goal is to find the partials of the weights with respect to the cost, or the partials of the cost with respect to the weights, and the partials with respect to the biases, right? The way that our automatic gradients are going to work is just with liberal use of the chain. So we're going to consider, if we go back to A here, we're going to consider this as a composition of a bunch of functions, right? So instead of ReLU being the only explicit function call here, we're going to have a ReLU, and then we'll just have an add function here. And then we'll have like a multiply function here, right? So we're going to end up with a bunch of function calls, right? And our goal, remember, is to find, here, we can actually, right, for now we can ignore the C's and stuff. If we're just looking at this, our goal is to find the partials of the inputs with respect, or the partials derivatives of the output with respect to each of these inputs. So just as a bit of an example here, let's flesh this out a bit more. So we have A here, and we can say that A of n is equal to ReLU of ZB. And then ZB is equal to add ZABN. And then we can say that ZA is equal to mul of WN and AN minus 1, right? So remember, our goal is to find the partials of these two with respect to A. But what we can do first is find here. So we know that this is a composition of a bunch of functions. So we can define we can define these in terms of chain rule. We know right now that we can get the partial derivative of ZA with respect to WN, right? Because this is matrix multiplication, that's just AN minus 1, right? Okay, and we know that we can get the partial of ZB with respect to ZA, right? That's just going to be 1, or like a 1 vector, right? Because this is just an addition. And then we also know that we can get the partial of AN with respect to ZB, and that's just like ReLU's derivative, right? And I'll just say like so. So if we look at what we have here, if we write this all out, we want to know what the partial of AN with respect to WN is, right? But if we write each of these terms out, we're going to get ZA WN multiplied by ZB ZA multiplied by AN ZB, right? This is just the chain, okay? And that just gives us our solution. So this is just a specific example where it's able to like explicitly write out each of these steps, but the power of having this computational graph is that we know to get C here, or to get AN here, we know what operation we had to do. So we know like the the output of AN could be going into any other function, and ZB could be coming from any other function, but we know how to add its own term to the gradient, right? We know, like, if we're taking a look at just this ZB-ZA term, we know that we can multiply this term in and add it to the next gradient. So, I don't know if this is totally making sense, but this is just called reverse mode automatic differentiation, and feel free to look up more about how this works, and hopefully the code makes more sense. But more generally, instead of the chain rule, what we're actually going to look at is the Jacobian vector product, or the vector Jacobian product. So let's say that we have some function f of x, right, where x is a vector. So f takes in a vector and produces a vector, and then we also have some function g of y, where y is a vector. So if we want to know it's fine. If we want to know f of g of y, right? If you recall back to like Calc 1, if this was just like f of g of x, where x is a variable, and we wanted to know the derivative with respect to x, then we would take f prime of g of x times g prime of x, right? But in this case, we want to know what's the gradient of y with respect to f, right? Okay, so if we have this set up, what we can say is that the gradient with respect to y of f is equal to the Jacobian of g. I believe it might actually be the Jacobian transpose times the gradient with respect to x of g. I believe so. And honestly, you don't fully need to know precisely like each individual component or even what the Jacobian is, but the TLDR is just that this is a way to do, this is like a multi-dimensional chain rule almost, if that makes sense. This Jacobian vector product here allows us to convert from the gradient with respect to one variable to a gradient with respect to another. So what we're going to be doing here, instead of just dealing with individual numbers here, when we have our vectors that we're chaining backwards, computing their each gradient, we're going to be computing its Jacobian vector product, right? Now, in most cases, this is actually going to be something we compute directly, right? Like, for example, ReLU, if you recall, of x is just max 0 and x. So if you pass a vector into ReLU, its inputs don't depend on each other, right? So because ReLU's inputs don't depend on each other, the Jacobian for a ReLU function will be only diagonal, right? You'll have and zeros everywhere else, right? It'll just be a diagonal. So that means that it's trivial to compute this Jacobian vector product, and there's no need to compute the Jacobian at all. So that's that. The goal, and hopefully this will make more sense as we actually start programming this here. So the first thing I'm going to do is actually loop through all of our variables here and clear their gradients. So if our variable, well, first off, what we're going to do is our current variable here is called like that. If our current variable does not require gradients, so if flag and env flag requires grad does not equal env flag requires grad, then this variable does not have a gradient whatsoever, right? And we can just continue. And now the other thing I'm going to add is if the current one is a parameter, then I'm also not going to clear it, and we'll get more into that later, but for now, don't worry about that too much. But here we're going to clear its gradient, and then I'm going to do is we know that the output is we know that the last variable in the program is the output, right? So, and that is the variable that we want to find our gradients with respect to. So I'm just going to fill its gradient with 1. In other words, that is giving us basically the gradient with respect to the gradient of each thing with respect to the sum of the final variable in our program, which in this case is perfectly fine. What you might want to do to make a more like complete robust system is to have is to explicitly have that last variable be just a single scalar if you're doing something like this. But for now, this is good enough. And then the other thing we're going to do, if you remember back to our computational graph, our topological order went this way. It went from inputs to outputs. But now we're finding gradients, so we need to go the other way. So I'm going to say, I'm going to do an I64. I equals program size minus 1. I is greater than or equal to 0, I minus minus. So now we're decrementing. We're going through the array backwards. And then we're just kind of a similar setup of grabbing each of our variables here. So our current is equal to our program vars I, and then our A equals current inputs 0, and B equals current inputs 1, like so. And then now we're just going to have the same switch statement, but what we're actually doing in each of these switch statements is different. So let me just clear all of this. Okay. Wait, did I not break after these? Ooh, that's a mistake. Let me break there. That would have been bad. Okay, so don't forget your breaks. So here in our function, or in our for loop here, where we're computing the gradients, the first thing I'm going to do is actually check if we need to do it at all. So if we only have the one input and that input doesn't require a gradient, then we can just skip this, right? Because the goal of each loop is to update the gradients of all of our inputs. Like at this point in the loop, we're assuming that current, its gradient is already what it is, and then we need to update the downstream gradients, or I guess the upstream gradients. I'm actually not sure. I don't know. So if num inputs equals 1 and a flags doesn't equal, then we can just continue. Like so. We can also do this if num inputs is 2 and a and b don't require gradients, we can also continue. But now here, so let's go to the simple case. So at each of these steps, we're going to take whatever we're going to add like the current gradient to our inputs gradient, and possibly modify depending on how we're doing it. So in the add function here, we're going to check if a requires gradient. Then we're going to mat add to a's gradient, current's gradient. And then same thing for b here, because it's adding. Again, this is just like if you imagine if we have some function add that takes an a and a b, actually we'll just, for now I'll just call it capital, or we'll just call it f, that takes an a and a b and returns a plus b, then our partial with respect to a is 1, our partial with respect to b is just 1. So if we're considering the fact that we have some larger, we wanted to find some cost with respect to a, that's going to be our partial with respect to a times our partial of the cost with respect to that, right? So because this term is just 1, we're just going to add to it the gradient that we already have at our current, right? This del C, del F term represents current gradient. And then same difference here for subtraction. We're just going to switch the add to a sub on B. And then for the mat multiplication, this is going to be, so here, I'm actually going to take this as well. So when we have, when we have the matrix multiplication here, what we want to do is, or actually here, let's consider if we have just some function, we'll call this one g of a and b, that's just a times b, right? Our partial of g with respect to a is b, and our partial of g with respect to b is just a, right? So in theory, when we're computing our partial c, partial a term, we take our current gradient and just multiply it by b, and vice versa for a. Because these are matrix multiplications, we're actually going to have to end up transposing one of them. So our matrix multiplication, we're going to add to a's gradient. So to get this here, we're going to add to a's gradient, we're going to multiply the current gradient times b's value, right? And I'm not going to zero the gradient because we're adding to it. And then I am going to transpose b's value. That's to get the shapes right. And then we're going to add to b's gradient a's value times current gradient. And then we're going to transpose a's value. Now that we've finished the basic operations here, I'm going to come back to our matrix implementation and actually fill in these three functions here. Although, so I've noticed we're also going to want to have our incoming gradient, because we need to multiply by that. And then in addition, here in the cross entropy, we have two inputs, so we are actually going to need two possible gradients that we can multiply and add into. So okay, let me update these function parameters. So now we have these. Come down here and paste them in. Okay. So our ReLU one, this is the simplest one. If you remember, ReLU was just the max of 0 and in data. So here, let me check that. And then we're also going to have to check for the gradient shape. And then here in out data, we're going to plus. So if in data is greater than or equal to 0, is greater than 0, then we're going to add the gradient. If it's not, we're just going to add nothing. We're going to add 0. And then, okay, so that's that. That's the ReLU. And then for the cross entropy, we're going to take first, we're going to have to check the size of each of these. Although I am going to make these optional arguments, so like the caller could make either of these null. And that's because oftentimes you don't need to find the gradient with respect to Q of the cross entropy, or with respect to P. So, but we'll call this P grad, and then this will be P grad as well. Okay, so then if you recall our cross entropy function here, it took P, which was an expected probability distribution, and Q, which was the actual probability distribution. And the cost for that was P times the log of, that is not a Q, times the log of Q, right? So if we are looking at our partials here, our partial with respect to P is just going to be negative ln of Q. And then our partial with respect to Q is going to be negative P over Q, like that, okay? So when we're doing, in this if statement here, we need to compute the partial with respect to P. First, let me grab the size of this. So we're going to go for I less than size, and our P grad, we're going to add to it, it's negative ln of Q, Q data, times the incoming gradients data, like so. And then if Q grad is not null, we're going to check the size again. And then here we're going to go for I equals 0, I less than size. If we're going to say that our Q grad at I will add to that negative P data I over Q data I times grad data I. We should probably do some check to make sure Q is not 0. Probably. I don't think we're going to run into that with what we're doing today, but again, for completeness. And then, so the softmax is a weird one. If you recall from earlier, the softmax of like some term I is going to be e to the a of I over, sorry, the sum, we'll say the sum of j, e to the a sub j, right? So because of this, in the ReLU and the softmax, there was no interdependence between variables in the inputs. So like the first variable in the output vector only depended on the first variable in the input vector, and so on. But with the softmax, because of the sum term, all of the variables depend on all of the other variables. And this means that our Jacobian, the Jacobian of the softmax function is not actually, is not diagonal, right? It has stuff everywhere. So when we're going to calculate the vector Jacobian product, what I'm going to do, and I don't know if this is actually the smartest thing to do. I'm sure you could calculate it directly, but just for the sake of making my life easier right now for this video, I'm just going to calculate the Jacobian directly, and then we're going to multiply the Jacobian to get the final thing. So for what we're going to do here, I'm going to call our matrix Jacobian. And first thing we need to do is say, oh, and also I should say, so the Jacobian of the softmax is just along the diagonal. It's the output, which I'll call S times 1 minus the output S. And then everywhere else, so that's along the diagonal. And then everywhere else, it's the output at, like, it's the output of the 1 times 1 or times negative output at j, right? Where like I is the row and j is the column, or something like that. I mean, it's equal to its transpose, so the order doesn't actually matter. But the output, it has to be a vector for this to work. So I'm going to say if the rows doesn't equal 1 and the columns doesn't equal 1, then it's invalid. We're not dealing with that. And that's also why this function takes the output instead of the input to the softmax, because it's easier to calculate the Jacobian that way. And then we're going to say that the size is whatever the size of the vector is. So that's the max of the softmax. If it's a row vector, it's the number. If it's a row vector, it's the number of the columns. If it's a column vector, it's the number of rows. Either way, because we've already checked that it's a vector, it's just going to be the max. And then we're going to create onto our Scratch arena n by n matrix. And then we're going to go for I equals 0, I less than size. For j equals 0, j is less than size. Jacobian data at I plus, or we'll say at j plus I times size is equal to I equals j, or well, it's actually, so it's going to be soft max out at I times either 1 or 0, right? You can see like this term could be 0, right? So I'm going to do that same trick again where I'm using the Boolean output directly as a number here. So I equals j minus softmax out at j. Out data. Okay, so that's that. And then we're going to say, well, first off, I'm going to return true here. And then we're going to say map mul the output, and then we want to multiply our Jacobian by our gradient and add it. Do not transpose. Although again, I mean technically I think you would transpose there, but because it's square, it does not matter. Alright, so that should be each of our gradient functions. So now we're going to come back down here. And remember, I already checked that earlier, this if statement here checks for unary functions, so we don't have to directly check if A requires grad. We're just going to call our mat relu add gradient, and we're going to add to A's gradient, where the input to it was A's value. And our current gradient is that. Okay. Softmax, similar story. Mat softmax add grad. And that's going to take A's grad as the output. The softmax out is actually our current value, and then our current gradient as well. That's that. And then for cross entropy here, we're gonna have to check. So if A flags, here, I'll just copy this. So actually no, we'll say, I'm gonna say our model P equals A and Q equals B. So if P, although actually because our function checks for null, if we have a model variable that does not require a gradient, its grad variable is just going to be null anyways. So I'm just going to call this function directly, and it'll take p's gradient, q's gradient, pq, and then current's gradient. Oh, actually, this is p value and q value. All right, and that should be it for the compute gradients function. So let's recall, we were given some computational graph here. The function program compile topologically sorted the directed acyclic graph to give us a list of variables in the order that they need to be executed, right? And then model program compute looped through each variable and computed its output, right? Model program compute grads went through in reverse topological order. It went from bottom to top of our list, our tree here, and our graph, and computed the gradient of each function that requires the gradient with respect to the output variable, assuming that our actual output is the sum of the output vector. Are you still with me? All right. Now that we've done that, we are finally ready to actually make our model, okay? I needed a glass of water, though. All right, so we have done, basically, here, if I go back to here, we have done the math. We have been able to find gradients. Now, all that's left is like the glue layer. All that's left is combining everything into one, like, slightly easier to use interface, and then actually making a model and training it, right? So I have these functions here, and we're going to take them and implement them like we always do. So our create function here, for now, all this will do is literally just push the model onto the arena and return it, because there's nothing in the model that we need to initialize right now. Now, right now, this is actually, this is an example of why I really like arenas, because everything that we're doing here in terms of like our matrices and our model variables are allocated on the arena. So when it's time to free the model context, right, you just have to like just clear that arena's lifetime, right? You don't have to go into traverse the tree and individually free each data variable you allocated for each model variable and stuff. So like, just to throw that out there. But if you were in a situation where your back end was GPU based or something, you might end up having to do that either way. So in your model create function, you might have to initialize some stuff, and you would probably want a corresponding model destroy function that cleans up everything. But as it is right now, all the memory cleanup we have to do is just like let the arena that the lifetime, that whatever model, like let the arena that you used to allocate the model on just die. Alright, so the model compile function, this one's pretty simple. We've got, if you recall, the model context has two programs, a forward program and a cost program. So I'm going to say if our model does have an output, in other words, we've made a valid program up to that point, I'm going to say that our model forward program is equal to model program create on the arena our model's output as the output variable. And then same deal here, if our cost is not null, then we can make a model cost program. That's also model program create, and that's going to take our cost as the output. And then feed forward, all feed forward is going to do is execute the forward program. Right. And that takes a pointer, so we'll do that. All right. So so the train function, obviously that's like the final thing, But what I'm going to do real quick is actually create our model in the main function. Probably going to take a while to actually climb up there. So here, I'll also have a function here called create MNIST model. This will take in an arena. This is just to have the model be created all in one place. So in our main function, here we drew that MNIST digit, and then I'm going to go ahead and create our model. And here, let me just look. So what we're going to do in this program is I'm going to call the create MNIST model function here, and that will populate all of the model variables for our model for the MNIST network. And then I'm going to call model compile to finalize that. And then what I'm going to do here actually is show what the output is before and after training. Although right now I'm just going to show the before output. So we'll say model feed forward. Or first off, we'll mem copy into model input value data train images data, and that's going to just be one training image times 784, like so, and then we'll say model feed forward, and then I'm going to print out the output. So this is pre-training output, and then we'll go I equals 0, I less than 10, I plus, and then we'll say f and model output value data I. Print f. Yeah, okay, so that's just to make sure that it all works. And then here, our actual model. So MNIST, it is here. If you recall, what we have for MNIST is a 28 by 28 handwritten digit, right? Here, we'll do 7, I guess. So this is 28 pixels here, 28 pixels here, and then our output is a 10 vector, or a 10 by 1 column vector of a probability distribution, right? We need some way to map that to that. So obviously we didn't do, if you wanted like the best, I feel like the state of the art probably would still be convolutional networks, maybe like a ResNet. But for right now, I'm just going to do a simple perceptron. So here's the model architecture. We're going to have 784 input. We'll do multiply by a weight and have a bias to get to a layer with 16. And then we're going to do the same thing, weight bias, and then also do, I'm going to do a residual connection here to show that our auto grad system is enabling for like more complex models than a simple perceptron could give you. And then our final 10 output here, another weight bias. So all of these ones are going to be ReLU, and then this one is going to be softmax, and then obviously our loss is going to be categorical cross entropy. Okay, let's get to it. So for our model here, I'm going to create our input variable. That's going to be mv create arena model, and we're going to have 784 rows, 1 column, and this is going to be mv flag input. And then I'm also just going to define all of the parameters at once. So we have 4 layers, so we need 3 weights and biases. So our first weight is going to be mv create model, and then this is going to be 16 by 784, I believe. And then mv flag requires grad, and then mv flag parameter. So that's going to be weight 1, weight 2. Weight 1 is going to be 16 by 16, and weight 2 is going to be 10 by 16. Now, obviously, this is quite verbose, So for an actual system, what I would probably do is have is you literally just make some lightweight, simple functions on top of the layer that we have here that allow you to create these things easier. Did I create a semicolon? So why are these biases are not being colored in? Yeah, so like you could just make a sequential function that takes in like an input size and an output size, but again, I'm just hard coding this for now. So now what we need to do, so our first layer here, I'm gonna have our Z0A, and that's gonna be MV matmul. Take the W1 input, no additional parameters. B is going to be MV add. It's going to take the arena of the model, and then it's going to add Z0A and B0 with no additional parameters. And then finally, our A0 is going to be MV ReLU. Z0B, no additional parameters. Okay, so like this is just our basic layer. It's the matrix multiplication. Multiply the weights, add the biases, ReLU. So we're going to do, for the second layer here, weight 1, A0, Z1A, B1. And then I'm actually going to call this one Z1C. And that's because of our residual connection here. So our model A0 is MV add arena model Z1C with A0, right? And then same thing for our final layer. This is going to take in weight 2 and A1, Z2, B2, Z2, and this is actually our output. So this is MV softmax, and then our flags will flag it as the output. Did I misspell output? It seems I misspelled it twice in the same way. Okay, it's been a long video. So output's there, and then I'm gonna have a desired output variable. I'll call this one Y, and that's gonna be MV create arena model 10 by 1 MV flag desired output, and then our model of our cost is MV cross entropy arena model cross entropy. So Y output, Y is the desired probability distribution, output is the actual probability distribution, and then flags will flag this one as our cost. That's the model. So let me just make sure that this compiles correctly. So what we should see is that I made a mistake somewhere. Oh, okay, it looks like I forgot to set outsize to 0 there. But now, oh wait, actually, okay. It looks like we're getting, oh shoot, you cannot see that under my head. It looks like we're getting just completely like uniform. And that's actually because we forgot to initialize our weights. So here, first off, I'm going to get rid of this so that the view is a bit easier. But what we need to do, I'm actually going to add another function here. I'll call this one matfillRand, and this will take an upper and a lower and fill the matrix with random numbers, because like your weights should be initialized randomly ideally. So we're going to go here, and then our each matrix is going to be prng rand f. Again, if you want to know how this random function number generator works, check out the video I made about that. And then, okay, so that's that. And then we're going to say in our create MNIST model function, each of these weights here, we're going to say mat fill rand, so on the value. And then This is, I believe it's called, it's either, I think it's Xavier initialization, but the bound that you use is, here, bound 0 is the square root of 6 over the sum of the layer sizes. So that's the first bound, and then second bound, and it's between negative bound and positive bound. Like so. So negative bound, or I think it's, it should be lower than upper. Lower. Okay. And then just do that for each of those. So now we should see some random variables. Okay. Let me compile this. All right. So you can see roughly uniform, but we're getting some nice random outputs here, right? So now that we're actually initializing this correctly, we need to make the training function, okay? So for this training, we're just going to do the simplest thing you can do. Well, basically the simplest thing you can do. And it's just called stochastic gradient descent. So what that means is that we're going to take all of our training examples, split it into batches, and then find the gradients for our parameters with respect to the cost for each of those every example in the batch, average that out, and then just directly subtract those gradients from our model. Now, I'm sure you can figure out if you want to do stochastic gradient descent with momentum, if you want to do root mean squared propagation or likely adaptive moment estimation, you can look that up. It's simple modifications we're going to be doing here today. But for right now, I'm just sticking with standard basic stochastic gradient descent. So I'm going to take, so we're going to have the number of examples that we're training on in this thing is going to be the training description. Actually, I'm just going to pull out each of these so that we don't have to type it as much. Alright, like so. And then we're going to say that our number of examples is the number of rows in our training images, and then we'll say that our input size is the number of columns in our training images, and we can also say that our number of test things is going to be our test images rows, like so. And then what I'm going to do is I'm going to grab a scratch arena here, because before we actually test on the input data, we want to shuffle it randomly so that it's like it can't learn what each batch is. So we're going to say mem, or we're going to say arena scratch get, no conflicts there. Remember to release the scratch arena. And then we're going to say that our training order here and push onto the array. This is just going to be a list of like the order in which we're going to train it, and that's going to be number of examples. And then I'm just going to loop through real quick and fill this in. Okay, so now we're going to do, well, the first thing we should do, I forgot here. So we want to get the number of batches as well. So that's going to be the number of total examples over our batch size. And for now, honestly, I'm just going to kind of ignore the fact that like our batch size might not be, or our number of examples might not be completely divisible by our batch size, and just we might lose some on the edges there. But no, so this is the main loop. We're going to, a training epoch is just like one iteration of all your training examples, basically. So if we have like 5 epochs per se, that means that we are training on every single image 5 times, right? So at the start of each epoch, I am going to shuffle our training order around. So to do that, I'm going to say, and honestly, you might be able to get away with doing num examples over 2. I don't fully know the best way to shuffle an array, but I'm just going to take this, and I'm going to modulo a number of examples. If you know anything about random number generation, you know that this theoretically, technically won't be uniform, unless if num examples is a power of 2, I believe, but I don't care right now. So we're going to, just to swap these real quick, we're going to take training order B, set training order B at B to training order at A, and then training order at A equals 10. Okay. Quick swap 2 random variables, randomize the order. Now we're going to go for the batches. So we're going to say for batch equals 0, batch less than num batches, batch plus plus, and then yeah, it should be it. So at the start of a batch, we want to clear all the gradients for the parameters, and then at the end of the batch, we want to update the parameters. So at the start here, what I'm going to do is go loop through the model's cost program, and then we're going to take each parameter and clear its gradient. So if model if the current flags is then we're going to map clear current grad. Now if you recall earlier when we were doing the compute gradients function, that I don't actually clear the gradient if it's a parameter. So that means that during our training batch, parameters won't have their gradients cleared, and they'll accumulate all of it. And then at the end, we can scale down by the batch size to get the average gradient for all of those training examples, right? True gradient descent, which would have you average over every single training example. But stochastic gradient descent does the batches thing, and it's good enough. And far, far more computationally efficient. Now, I don't know if you could actually run into an issue. I don't see a scenario in which a variable would depend on a parameter, like a parameter would not be a leaf node, but maybe that could happen. I don't know. Let me know in the comments if you're still with me in this video. So, cleared all the parameters. Now what we need to do is go through all of our training examples in the batch. So I'm going to say for I equals 0, I is less than training desk batch size, I plus plus, and we're going to say that our index is going to be, or I'll say that our order index is going to be our batch times our batch size plus I, and then our actual index is training order index, like so. And then what we need to do is copy the actual example. So I'm going to mem copy into model input value data the training example. So it's going to be the train images dot data plus the index times 784. Because it's pointer arithmetic, I don't have to multiply by size. But here, because this is a number of bytes, I will have to multiply by size, and I cannot hardcode 784. This is going to be input size, and I have not made that variable yet, but we will in a second. Oh, I did make that variable, actually. That's fun. We should do output size as well. Because now we basically do the same thing for the model's output. And if you could not tell, this is kind of not the, this is probably not the best way to like encode training data, because we're largely just hard coding it, but it is good enough for this example, and I'm sure like you can come up with a better way to actually do it yourself. So now what we do is we need to run the forward program for the model's cost program. We need to compute the cost, and then we need to compute its gradients. Other thing I'm going to do during the batch is calculate the average cost. This is just so we can have a bit of a metric as to how the model is doing during training. You know, if you you can oftentimes tell if you've made a bug when your cost is going crazy, or if it's NaN, which both happened when I was working on this video. So don't get discouraged. Programming and machine learning can be absolute hell. But so that's that. We load in an example, compute the gradients, and then after the entire batch is over, we're going to loop through all of the parameters again. So here, this time we have a bit more computation to do, so I'm going to check. I'm going to actually just continue if it's not a parameter. And then we're going to do, we're going to say that well, first off, we need to scale the current gradient by the learning rate, which is going to be part of the training description. So the learning rate over the batch size, which is also in the training description. So this is the batch size. Well, like the learning rate is just something you multiply your changes by to make it a little bit more tame, and then obviously averaging the batch size. And then we're going to say mat sub the current value. And if you're confused about why we're subtracting instead of adding here, is because gradients point in the direction of steepest ascent. We want to go in the direction of steepest descent, so we need to subtract instead of add. We've officially hit 1,000 lines of code as well. Okay, so that is the training loop. But one thing I am going to add here after we're done with all the training is to go through all the testing examples. Actually, the first thing we should do is here, I'm just going to print some debug information. So we're going to say run epoch, whatever out of whatever, batch, whatever out of whatever, and then our average cost is whatever. We'll say .4f, and then I'm going to use \r, the carriage return, to reset the line, and that's also why I'm explicitly putting precision on each of those so that it'll look clean when we're doing it. And epoch plus 1 epochs, and then we're going to go batch also plus 1 batch, or no, that's actually just a variable. You have num batches, and then our cost is just our average cost. So displaying the cost of like the last batch of, or like the most recent batch as the printing, and then this is at the end, so I'll print a new line here, and then here we're going to go through all of our testing examples to get our test accuracy. So I'm going to say, actually first what I'm going to do, I'm going to add one more function to our matrix thing, and I'll call this one argmax. And I forget I believe that in like actual libraries, argmax will like do along a specific axis or something, but because we're dealing with vectors here, I'm just gonna get the largest index in the overall matrix, just because that's easier. And then max is equal to -infinity, and then max I equals 0 if mat data I is greater than max. then actually we can just say mat data max I equals I, and then return max I. This is because we're just going to assume that whatever is the highest probability is what the number that the model is choosing. So when we're testing the accuracy, we can compare the argmax of the output to the argmax of the desired output. Okay, so now we're going to do for I equals 0, I is less than num tests, I plus plus, and then we're going to have our average. Well, for accuracy, we're going to need num correct, and then we're going to do average cost as well. So for that, we're going to do, first we need to load an example into our model. I'm going to take this code to load that, but we're going to have to copy, instead of train, this is going to be test labels and test images, and we do not need to do the backwards pass here. So we're just going to have model program compute, and I am going to use the cost program here because this computes the output in addition to the cost. So the average cost will plus equal the mat sum of the model cost value, and then our num correct will plus equal if the argmax of the output value equals the argmax of the desired output value, like so. And that should do it for that. So then our average cost divided by equals our number of tests, and then we can print test accuracy, or we can say like test completed. Accuracy was, we can say like 40 out of, or like 10, I'll say 5D out of 5D, which would be 2F%, let's say 1F%, and then average cost is .4F, and then that can be a new line. This is just to display the results of the test. And then we're going to have num correct over num tests, and then this is F32 num correct over num tests times 100, and then average cost. And that, my friends, finally brings us to what I can only hope to be a triumphant end here. So this is the pre-training output. Now we need to make a model training description, and this will be, we pull it up, so dot train images equals train images, dot train labels equals train labels, dot test, here we're going to just copy these two lines, tests, and then dot epochs will go for 3, and then we'll say our batch size is 50 and our learning rate is that. But I'm actually going to do slightly higher learning rate. So okay, that was the pre-trained output. Now we're going to say model train the model with that training description, and then we're going to say that was the pre-training output. We'll say this is the post-training output. And I'm going to add a new line because it didn't fit all on the screen. Or actually, you know what might be better is if instead we just go for like .2f. Give it a little more space. Okay, so that should do it. So I'm going to compile this. Actually, I'm not super confident. We're going to compile with debug information and address sanitizer. Alright, I figured out the issue here. This should be the desired output when we're when we're setting up our inputs here, we don't actually want to override the output. That makes no sense. So that explains why we weren't getting any cost. Not explain why. Oh. Okay. So now we compile this with optimizations. Let it train. Alright, I have found the issue. It was in the matrix multiplication function. These two lines here still use transpose A because I did not correctly copy the two lines. So, now, what we can do, I'm going to compile main.c with optimizations on. And you will see that our average cost dramatically decreases. After just one epoch of training, we're already at 86% accuracy. And now look at this. If I go back here and draw our initial input, if you recall, it's a 4. Excuse me. And now, after training, so the probability distribution we want to see is a 1 in the 4th index and a 0 everywhere else. And after training, 0, 1, 2, 3, 4, and my head is completely covering it. Look at that. 89% confident. Come on. Like, that's pretty cool. That is pretty cool.